Welcome you all to the Research Spark YouTube channel. Today we are going to talk about the fourth unit, that is the application of the linear ICs. Here is the syllabus for the fourth unit. Basically, here if you check all these contents are related to the application of integrated circuits that we have discussed in the entire different unit 1, 2, 3. In this session, we are going to mainly focus on the following the topics: your summing, subtractor, then the integrator, differentiator, difference amplifier, instrumentation amplifier, voltage to current converter, current to voltage converter. So let's talk about the summing and subtractor amplifier. So basically here you can see the example, summing example. So here we are using the operational amplifier, that is IC741. So this is the one of the application of IC741. Here there are two different inputs, that is inverting and non-inverting. So through the inverting terminal itself, we are giving the three different voltages, that is V1, V2 and V3. So in the output, we will get the addition of all these three voltage. So this is exactly the process to add the different signals. So at the same time, we can also use the uh, non-inverting inverting terminal as well. So here if you will try to solve the equations that by using the KVL or KCL. So if you use the KCL, then I1, I2 and I3, the addition of all these three current will be equal to I1. And so finally you will get the equation for voltage output will be equal to minus of RF divided by R1 into V1 and RF divided by R2 V2 and plus of RF divided by R3 V3. So in this way, we'll get the addition of all these three input voltages. That is why this is called addition or the summing amplifier. Similarly here, either some voltage may have the out of phase, that is phase difference may be of 180. In that case, the signal may be subtracted. Another way is that we can have the different inputs through the different terminals, that is the inverting and non-inverting terminal. In that case also we'll get the output, the difference of both voltages. And then let's talk about the integrator and differentiator circuit. So here just see in the left side, this is the IC741 based integrator circuit. So the primary objective to design the integrated circuit is to get the integration of the input voltage. So what is our input voltage? That is our V1. And if you will check the output voltage, then this is equal to the Vc minus of 1 divided by R1 C2, and then integration of your input voltage, that is V1t with respect to dt. So whatever is input voltage will you supply, correspondingly we will get the integrated output voltage. So how is it happening? Because of the capacitor, since the capacitor itself have the voltage, and that voltage will be the integration of the V of dt. Similarly, now differentiator may contain the capacitor in the main circuit, not in feedback. So R2 is in feedback in the differentiator circuit and capacitor in the input side. And if we'll find out the output voltage, then here it will be equal to minus of R2 C1 and derivative of V1 divided by dt. So that is why this is called the differentiator circuit, since we are going to obtain the output voltage, that will be the derivative, that is differentiation of the V1, that is the input voltage. So here just you can remember, like if your capacitor is in the input side, then it will act as a differentiator, and if your capacitor is in the feedback, then it will consider as a integrated circuit. Now next is the difference amplifier. So here again, here we are giving the different inputs, that is V1 and V2 through the different terminals, inverting and the non-inverting terminals. So again, using the KVL, you can find out the voltage at the non-inverting terminal, and that will be same equal to the inverting terminal, and in this manner you can find out the V output. So once you will find out the V output, then you will get the 1 plus of R2 by R1 into R4 by R3 and 1 plus R4 by R3 into V1 minus R2 by R1 into V1. However, there may be the special case where R4 divided by R3 is equal to the R2 by R1. If it is so, then finally you will get the output voltage that will be equal to R2 by R1 into V12 by minus V1. So this is the actually it will be the simple equation. So in this manner we'll get the difference of the two different inputs. So this is the simple the KVL circuits only. So primary objective, like while you are solving these type of operational amplifier circuits, don't forget to use always since there is a huge impedance in between the inverting and non-inverting terminals, so potential will always be same. So this is the primary one thing. So first find out the potential at either any of the terminals, and then it will be equal, and then use the KCL method to find out your current or output voltage. Then instrumentation amplifier, actually our primary target is to get the infinite amplification or the gain, and the inputs should be the very high, but this is not actually the ideal case. In practical we not achieve, sometimes we are unable to achieve using the operational amplifier. So here we are going to design the instrumentation amplifier to achieve our objective. So if here we will check, then we'll have the A1, A2, and A3, three different operational amplifier. So the output of the first, that is A1, will be V11 plus I1R2, and the output of second A2, that will be V12 minus I1R2. And finally, your final output will be equal to R4 by R3 into VO2 minus VO1. So if you use this equation, you will get the final equation, and that will have the advantage of the infinite huge gain. Since the input signal voltage are applied directly to the non-inverting terminals of A1 and A2, the input impedance is also very high, ideally infinite, which is the one desirable characteristic of the instrumentation amplifier. Now let's talk about the current to voltage and voltage to current converter. So the primary objective of this current to voltage is to give the current in the input side and got the output in the output side, voltage in the output side, so that it can convert from current source to the voltage. So how will you get? So simply input side, you can just check our input will be equal to Vi by I1. It may be almost equal to 0, and so since there is a no flow of current inside the operational amplifier, so IT will be equal to I1 is equal to I of S. So now finally we'll get the output that will be equal to I2 into RF. So this is your output voltage is depending on the current source that we have applied, that is IS. So IS into RF. So this is now how we can get the output voltage, which will depending on the input current. Similarly, in the right side, we can observe the voltage to current converter. So input is voltage, that is the V1, and output will be the current, that is the IL. So how to find? Can use the KVL equation, and so we'll get the V1 minus I1 IL ZL divided by R1, that is the current. Since no current will flow through the operational amplifier, so just find out the I1 and I2, so that will be equal to the IL into ZL minus VO divided by R. Now further, if we'll solve for VO minus IL ZL, then we will get the equation, that is the IL into RF ZL divided by R1 R3 minus 1 minus ZL by R2, which will be equal to a V1 into RF divided by R1 R3. Now in order to make IL impedance of this ZL, we can use the RF divided by R1 R3 is equal to 1 by R2, and we can also write the IL is equal to minus of V1 RF by R1 into R3, which will be simply equal to minus of V1 by R2. So here you can see your IL is depending on the input voltage, that is V1 divided by R of 2. So R of 2 is the resistance which we have applied in the feedback. So finally current output, that is IL, is only depending on the two things, that is input voltage and the impedance which is applied in the feedback. So this is also being used as a voltage to current converter. So that's all in this session. In the next another second session, we will see about the comparators, schematic triggers, and non-sinusoidal oscillators, then filters, and then lastly we'll see the waveform generators. Thank you for listening. If you have any doubts, please drop your comments. Thank you.